Let me introduce our first topic. It's going to be Tailor Welded Blanks. We have 3 speakers. The first is Mike Daniel. He's a structures technical specialist for Ford Motor Company. He's worked for Ford Motor for 24 years and has recently completed the launching of the F-Series aluminum structure. Our second speaker is going to be Dawn Sebleski. Hey, got it. She is the account manager with TWB Company. In her role, she works with automotive design engineers to incorporate tailor-welded solutions for improved part performance and achievement of lightweighting targets. Applications include both steel and aluminum solutions. Dawn earned a bachelor's degree of science in metallurgical engineering from The Ohio State University. She began her career with Worthington Steel as plant metallurgist before becoming a technical services manager at Worthington's automotive business unit. Dawn has over 15 years of experience in the metals and automotive industries. And then last but not least, we have Beck Oines. Beck has 5 years in the automotive industry at Ford Motor Company, 2 years in aluminum development, and he has a Bachelor of Science degree in aerospace engineering from the University of Michigan. So, without further ado, I'm going to hand it over to Mike.
As Teresa said, my name is Mike Daniel from Ford Motor Company. I've been working on the aluminum for about as long as I have been with Ford. This presentation is about our next step in our not only lightweighting but cost savings, because everybody who deals in structures know we don't get any credit for anything. We just need to keep taking weight out and taking cost out with improved performance. We have one application coming out very soon of a tailor welded blank. It'll be on the new Expedition. Then we're working on another one which we'll touch on. Dawn's going to start the presentation. She's going to give a quick pitch of who TWB is. Then she's going to talk about what linear friction welding is for those who don't know, and then Beck will follow on with the rest of the presentation.
Well, thank you, Mike. Hello, and welcome to the conference. So today we will introduce you to TWB and aluminum friction stir welded blanks. We'll share with you a study that was completed on a next generation truck, and discuss with you the results of mechanical properties and stamping trial. So today, tailor welded blanks, tailor welded coils, and hot form tailor blanks are commonplace in traditional steel designs. There are over 50 body structure, closure, and frame applications where these products have been applied to reduce weight and improve safety in a cost-effective way. Today, these same benefits are available in aluminum designs. TWB is the global market leader in tailor welded solutions. In North America, we operate 10 facilities with the support of our parent companies, Worthington Industries, a leading materials processor, and Wisco Tailor Blanks, part of Wuhan Iron and Steel Company. Our footprint extends to the Asian and European regions, which allows us to develop and deploy tailored welded technology throughout the global automotive industry. We have 2 welding processes for the production of aluminum tailor welded blanks. Today, we will be discussing aluminum friction stir welded blanks. Our welding processes are laser and friction stir. Friction stir welding is a solid state welding process. The process is very similar to a milling operation, except instead of cutting material, we are forging it together. Think of it as an extrusion between 2 sheets of aluminum. There's a tool that rotates and plunges into an interface of 2 abutting sheets of aluminum. The rotating tool creates friction and causes severe plastic deformation, moving material across the seam. Heat is generated both from the friction and the deformation, locally softening the material but not melting it. The tool progresses along the seam, locally forging the material together. The tool itself is specifically engineered with pin and shoulder features to control the metal flow into and across the seam. The result of the welding process is a weld seam with a fine-grained microstructure and excellent mechanical properties. The weld exhibits a smooth 12 millimeter transition across the seam and the top surface contains a swirl pattern left behind by the tool's shoulder. One of the benefits of friction stir welding is that there are no weld solidification effects, such as porosity, shrinkage, or hot cracking. Lubricants are not removed prior to welding, and they simply dissipate from the weld seam during welding. Friction stir welding is also considered a green technology as it has a low energy consumption, uses no consumable tools and no shielding gas, and produces no hazardous fumes. It is also proving to be a significant enabler of cost-effective lightweighting, and as you will see in this presentation, reduces aluminum usage. A typical friction stir weld microstructure is shown here. It consists of a stir zone, a thermomechanical affected zone, a heat affected zone, and the parent material. The stir zone is in the center of the weld where the pin has traversed. This region has fully recrystallized, the grain structure is fully equiaxed, and a finer grain than the parent material. The thermomechanical affected zone is alongside the stir zone. This region has seen a lower strain and lower temperature than the stir zone, thus it has not recrystallized. The microstructure in this region is elongated. The heat-affected zone is the region where there's no deformation that's occurred. However, this area may have been subjected to a thermal cycle. Typically, we measure consistent or slightly increased hardness from the parent material and across the weld seam. However, this can vary depending upon the alloys that we are joining. It is also notable that in the same gauge to same gauge weld seam, the profile across the weld seam is uniform. So friction stir welding has been used successfully for years in aerospace, trailer manufacturing, and shipbuilding applications. However, the demands for these industries are significantly different than the demands for automotive. Automotive applications are thinner and require high speeds to support high volume manufacturing. Through a Department of Energy collaboration, these technical hurdles have recently been overcome. The collaboration resulted in the commercialization of high-speed friction stir welding. Whereas only several years ago, speeds of 1 meter per minute were common, speeds of 6 meters per minute are now obtainable. Also, sheets as thin as 0.8 millimeters have been successfully joined. This technology is applicable to curvilinear, also known as 2D welding, joining of all the common automotive aluminum alloys, mixed alloys, and magnesium sheet. The benefits of an aluminum tailored blank are very similar to traditional steel blanks. They include part consolidation, part optimization, and improved material utilization. By consolidating components such as a door inner panel to a hinge reinforcement, component weight is reduced, manufacturing costs are lowered, and dimensional control is improved. Part consolidation enables an engineer to select the optimum gauge and alloy in the ideal area of the part, reducing component weight and improving part performance. Because we are blanking prior to welding, blank nesting is also optimized, which improves material utilization. These considerations allow you to use aluminum more efficiently and reduce the cost of an aluminum solution. At this time, we are using both friction stir welding and laser welding for the production of aluminum tailor welded blanks. Although laser welding is suitable for 5000 series and low copper, lower strength 6000 series, it is not yet developed for the higher copper, higher strength 6000 series. There are two significant technological hurdles at this time for welding these heat-treatable alloys. First, the chemistry makes them susceptible to hot cracking when molten aluminum is solidified. And second, softening in the weld seam occurs in laser welding that does not recover during subsequent heat treating. So the project with Ford is a heat-treatable 6000 series alloy. Thus, our technology choice at this time was friction stir welding. At this point, I'd like to turn it over to Beck, who will explain the specific development steps that the Ford team took to validate the process for an underbody application.
All right, thank you, Don. As Mike and Don touched on, I will go through the application study for our underbody component, in which we utilized a linear friction stir weld to combine two same gauge 6000 series blanks. And the benefit of this was a significant increase in material utilization. So several key mechanical property tests were conducted, the first of which was tensile tests taken transverse to the weld seam. The data is shown here, and as you can see, the welded material shown in blue has equivalent yield strength to the parent material shown in red. We do see a slight decrease in ultimate tensile strength and a decrease in elongation in the welded samples. Not shown here are the properties of the weld seam along the weld, which do compare near equivalently to the parent material. Something to note is that the friction stir weld in this application compares favorably to aluminum gas metal arc welding, which potentially decreases yield strength and ultimate tensile strength by up to or over 50%. Next, we studied micro indentation hardness. The top is a graph of a sample with measurements taken at 1/4, halfway, and 3/4 up the thickness of the sample, of the cross-section. And the bottom is a color map of the micro hardness for another sample. So you can see in the bottom graph that significant mixing of the material occurs. However, in this application, there's no distinct heat-affected zone that is characterized by a decrease or change in the micro hardness. Rolling direction was studied using a tensile test as well to understand its effects on the welded material. For the yield strength, in all orientations we welded, and these orientations were with the rolling direction along, transverse, and a combination in a single combined blank to be transverse and along, the yield strength was equivalent to parent material for all orientations. We see that consistent with the previous tensile data, that elongation is decreased here as well. So the same test was conducted in terms of orientation of rolling direction for material that was subject to a heat treatment process. When the material is heat treated, there's a significant increase in yield strength, and that same increase is seen for the material that has been welded. So this means that in service, in a heat treated part, we will not see or sacrifice any strength of the material. We also see a decrease in elongation here as well. This will not affect the parts in service. Limited dome height was also tested to understand the formability of the welded material. And again, the same three combinations of rolling direction orientation were measured. The parent material is shown on the left, and the data to the right for all orientations measured both weld face down towards the punch and weld face up away from the punch shows good acceptable formability. So in high volume production, mechanical joining is automated. So it is critical that we ensure that the joining always falls in the parent material after accommodating all the process variation. In this specific application, in the underbody, corrosion is especially important. So we tested corrosion on 6,000 series samples with the friction stir weld, and we left it uncoated. We saw that there was no objectionable surface corrosion on or near the welds. We also tested for E-coat adhesion and found that the welded area meets our E-coat adhesion requirements. So after performing our mechanical properties test, our next step was a stamping trial. We actually conducted 3 stamping trials. The first was a small prototype tool stamping trial. The next was a small production tool stamping trial. And the third was a run-at-rate larger trial on the production tool. For each trial, we were able to achieve good parts, good formation, and you can see in the picture that there is a good amount of draw and formation to this part. No defects were seen coming from the parts themselves or the welded area on the parts. However, we did see splitting, which I'll cover more in depth on the next slide, and it all originated from the edge of the blank, and the most propagation was seen on the run-at-rate stamping trial. So as we demonstrated during stamping, the weld line in its position is very critical. When the blanks are manufactured, the friction stir weld tool plunges into the blanks a couple of millimeters from the edge of the blank. As it welds the blank, it then exits the opposite end the same distance from the edge of the blanks. So as a result, there is about 2 to 3 millimeters of unwelded material followed by a notch that was created by the tool. And this notch is actually a stress riser. If this stress riser is not kept in an area of low strain, we can see splitting and it can potentially propagate. which we again saw at the trials, specifically at the run and rate trial. CAE confirmed what we saw at the stamping trial, that high strain is seen at the notch at the edge of the blank. The solution to this is to remove the notch with a cutout, which removes the stress riser and the unwelded material. We use CAE to validate that this will enable us to process the panels at production speed without a risk of splitting, and this enables us to use a friction stir welded blank in a high volume application such as this. Another solution would be to move the weld line to somewhere where the notches are not in an area with transverse metal flow. However, you may then lose some of your material optimization or another issue. In summary, with the development work we have conducted with TWB and with the application study we have completed, we have validated that friction stir welded aluminum tailor welded blanks are feasible for high volume production. We've also seen that the mechanical properties of the friction stir weld are especially beneficial for 6000 series aluminum. With our stamping trial and our CAE evaluation, we have noted that the friction stir weld seam, where it starts and stops, is critical and must be kept in an area of low strain or removed from the blank. And finally, we have additional plant trials planned for the second quarter of this year. And before we conclude, we'd like to recognize and thank everyone who was helpful and contributed to this project, the Arconic team, the Ford team, the TWB team, and a special thanks to Yuri Havansky from Brigham Young University. So with that, we'll open for questions. Thank you.